Assalamu alaikum, dear students. Let's move to the next part of chemical kinetics. In this part, we'll discuss how rate of reaction is affected by temperature using some graphs, which are nothing but we call them as Maxwell Boltzmann's distribution curves. Now, in previous session, we have discussed increase in temperature increases the rate of reaction, and with the increase in temperature by 10 degrees Celsius or 10 Kelvin, rate of reaction almost doubles. Now, what's the reason behind why increase in temperature increases the rate of reaction? What happens actually by which a rate of reaction is increasing? That we'll discuss in this session based on these graphs, right? Now, to understand that thing, we have a graph over here where I have taken potential energy along the y axis, and it is a reaction mechanism taken along x axis, right? Two reactants are there, H2 and I2. Whenever hydrogen and iodine react, they produce hydrogen iodide, right? Now here, this two reactants are shown at this point, okay? Their energy has been shown from this point, means this is the zero origin part and the reactants are having this much energy. It is nothing but the meaning is whenever to start a reaction, those reactants must have some minimum amount of energy to react, right? Always when you are carrying out some reaction, those reactants which you are using, जो reactants आप यूज कर रहे हैं रिएक्शन में, उनके पास कम से कम कुछ एनर्जी चाहिए ताकि वो रिएक्ट हो सके, उसको हम बोलते हैं पोटेंशियल एनर्जी. The minimum amount of energy required by the reactants to react is called as potential energy, right? इसके बाद क्या होता है, उतनी एनर्जी के जरिए से वो रिएक्ट होना स्टार्ट करेंगे, राइट? जब ये रिएक्ट होंगे तो उनके पास और थोड़ी और एनर्जी चाहिए ताकि वो एक लेवल पे पहुंच सके. They need to reach over here. Okay, in the surface chemistry part also this has been discussed with respect to catalysis. तो यहाँ पे भी वही है, रिएक्टेंट्स रिएक्ट हो जाएंगे, रिएक्ट होने के बाद जब प्रोडक्ट फॉर्म करना रहता है तो प्रोडक्ट फॉर्म करने से पहले उनको एक इंटरमीडिएट फॉर्म करना रहता है, यानी कि एक एक्टिवेटेड कॉम्प्लेक्स, एक इंटरमीडिएट, एक अनस्टेबल स्पीशीज जो इमीडिएटली प्रोडक्ट में चेंज हो जाता है. तो वो इंटरमीडिएट या एक्टिवेटेड कॉम्प्लेक्स यहाँ पे फॉर्म होता है, राइट? तो यहाँ पे फॉर्म होता है तो मतलब यहाँ तक पहुंचना पड़ेगा रिएक्टेंट्स को, यहाँ तक पहुंचना पड़ता है, मतलब इतनी एनर्जी और एक्स्ट्रा एनर्जी चाहिए एक्टिवेटेड कॉम्प्लेक्स फॉर्म करने के लिए, राइट? सो द एक्स्ट्रा अमाउंट ऑफ एनर्जी, the minimum extra amount of energy required by the reactants to form the activated complex is called activation energy, right? For different reactions it will be less or more. So this extra amount of energy required by the reactants to form the activated complex, we call it as activation energy, denoted by EA, right? तो यहाँ पे फॉर्म होता है एक्टिवेटेड कॉम्प्लेक्स या इंटरमीडिएट. ओके, तो यहां से यहां तक क्या था, ये था पोटेंशियल एनर्जी. यहां से यहां क्या है, ये है एक्टिवेशन एनर्जी. अब ये दोनों जब मिलाएंगे, यानी कि यहां से यहां तक, मीन्स फ्रॉम हियर टू हियर, दिस इज व्हाट वी कॉल इज थ्रेशोल्ड एनर्जी. Threshold energy is nothing but the sum of potential energy and activation energy, or it is the total energy required by the reactants to form or to reach the threshold barrier. इसको हम बोलते हैं threshold barrier. The total energy required by the reactants to reach the threshold barrier is called threshold energy. Okay. Now, initially this was their potential energy. We write del H1, and when the products are formed their energy has been lowered. देख सकते हैं यहाँ पे हायर एनर्जी वैल्यू है, यहाँ पे लोअर एनर्जी वैल्यू है. दिस विल बिकम H2. So H2 minus H1, you will get delta H, enthalpy change will be obtained, right? So this change in energy, the enthalpy change is there here. it shows that energy is lowered, so it is for exothermic. Sometimes product will be formed over here, that will be endothermic, right? Now here, so this is the way how reaction is taking place. Always whenever you talk about the reaction, this is the simple mechanism how the reactants react from the activated complex and convert into product. These are all the definitions of those terms. Potential energy, minimum energy required by reactants to react, activation energy, extra amount of energy required by reactants to form activated complex or intermediate. What is the activated complex? It is the intermediate formed at the threshold barrier. Threshold energies, the total energy required by reactants to reach the threshold barrier. Threshold energy is equal to potential energy plus activation energy. Now, during this process, what actually happens, how those molecules are reacting, how much energy those molecules are having, that can be explained by drawing Maxwell Boltzmann's distribution curve. In this graph, we will be taking fraction of molecules along y-axis and kinetic energy along x-axis. Fraction of molecules will represent by Ne by Nt, where Nt is total molecules participating in reaction, right? And N is molecules having energy E. यानी कि जितने भी हम रिएक्टेंट लेते हैं, पूरे के पूरे मॉलिक्यूल्स पूरे प्रोडक्ट में चेंज होना जरूरी नहीं है, एंड इट डजंट हैपन सो. ऐसे रिएक्टेंट मॉलिक्यूल्स जिसके पास एनर्जी है, मिनिमम काइनेटिक एनर्जी है, पोटेंशियल एनर्जी है, वही जाके वो रिएक्शन में पार्टिसिपेट करते हैं और फाइनली वही प्रोडक्ट में चेंज हो जाते हैं. तो यहाँ पे भी हम क्या कर रहे हैं, टोटल मॉलिक्यूल्स नहीं ले रहे हैं, वी आर टेकिंग फ्रैक्शन ऑफ मॉलिक्यूल्स, and that fraction of molecules denoted by Ne by Nt. Ne is molecules having energy E and Nt is total molecules, right? So when you plot the graph here, fraction of molecules against kinetic energy, you will find that there are increasing number of molecules having kinetic energy, right? There are increasing number of molecules having kinetic energy, and you will find a point over here. ये ऐसा पॉइंट है जहां पे मैक्सिमम नंबर ऑफ मॉलिक्यूल्स के पास उतनी एनर्जी है, इतनी काइनेटिक एनर्जी मैक्सिमम नंबर ऑफ मॉलिक्यूल्स के पास है. उससे पहले फ्रैक्शन ऑफ मॉलिक्यूल्स कम है और उसके बाद एनर्जी ज्यादा है लेकिन फ्रैक्शन ऑफ मॉलिक्यूल्स कम है. सो दिस पॉइंट where maximum fraction of molecules are having kinetic energy, we call it as most probable kinetic energy, right? Means here, अब जैसे कि फॉर एग्जाम्पल व्हेन यू स्टार्ट ए रेस, कोई रनिंग रेस स्टार्ट करते हैं तो शुरुआत में क्या है, मैक्सिमम प्लेयर्स अच्छा खासा भागते हैं, ओके. बाद में क्या हो जाता है, एक पर्टिकुलर पॉइंट तक बहुत सारे पार्टिसिपेंट्स रहेंगे जिसकी स्पीड सेम है, उससे पहले थोड़े कम रहती है लेकिन एक पर्टिकुलर पॉइंट पे सब एक लेवल पे पहुंच जाते हैं. बाद में क्या हो जाता है, जिसका स्टैमिना कम है वो स्लो स्लो होते जाते हैं और जो स्टैमिना ज्यादा रखते हैं वो फास्ट भागते ही जाते हैं, राइट? लेकिन जितनी एनर्जी ज्यादा होते जा रही है वो मॉलिक्यूल्स की क्वांटिटी भी कम होते जाएगी, राइट? सो एट ए पॉइंट यू विल हैव maximum number of fraction of molecules having kinetic energy, whereas with the increase in kinetic energy these fraction of molecules number will decrease, right? And finally at a particular point, say for example here, if I mark this as the activation energy, it is the extra amount of energy required to form activated complex, and once the activated complex is formed they will convert into product. So once the molecules reach this energy value, definitely they are going to convert into product, right? So if I compare these curves at two different temperatures like this, same graph, fraction of molecules, here kinetic energy, this curve is there at a temperature T degrees Celsius or T Kelvin, say it is T degrees Celsius, okay. Now it is reaching a particular maxima here, that energy we call it as most probable kinetic energy, and there are decreasing number of molecules, and once they reach this point we call it as energy of activation, and then once they get the energy of activation they convert into product because they form activated complex and convert into product, right? So when the temperature is raised by 10 degrees Celsius or 10 Kelvin, see what happens. The curve broadens out. Okay, कर्व का एरिया यहाँ पे चेक करो आप, ऑलमोस्ट दोनों का एरिया कांस्टेंट होना है, लेकिन सिर्फ होता क्या है, यहाँ पे हाइट हो गई थी, यहाँ पे ये ब्रॉड हो जा रहा है, स्प्रेड हो जा रहा है, राइट? मतलब मोस्ट प्रोबेबल काइनेटिक एनर्जी पॉइंट आपको यहाँ पे मिलेगा जो पहले से कम है, लेकिन ये कर्व थोड़ा राइट साइड की तरफ शिफ्ट हो जाता है, मीन्स you can find more number of molecules are there, fraction of molecules are there having higher kinetic energy now, right? So you can see over here the molecules were less, but here for the t plus 10 graph the molecules are more in number, and when you check this point, very important part, at this point when you can see earlier only these many molecules were having kinetic energy. Now at higher temperature by 10 degrees Celsius, you can find some more number of molecules participating or having activation energy EA. मतलब हो गया क्या, टेम्परेचर 10 डिग्री सेल्सियस बढ़ाने से fraction of molecules having activation energy has increased, and once that increases definitely product will be formed more and rate of reaction also increases. So this was the part where fraction of molecules were having kinetic energy EA at T degree Celsius, and this is the extra part added of fraction of molecules having EA at T plus 10 degrees Celsius, right? So this area shows fraction of additional molecules which react at T plus 10 degrees Celsius. यानी कि टेम्परेचर बढ़ाने से आप और जरा पार्टिसिपेंट्स को बढ़ाए जैसा है, जैसे कि कोई कंपटीशन में कोई पार्टिसिपेट नहीं कर रहा है, कोई आपके टीचर आके एंकरेज कर रहे हैं, तो पार्टिसिपेंट्स क्या हो जाते हैं, थोड़े डबल हो जाते हैं। तो यहाँ पे भी वही हो रहा है, टेम्परेचर बढ़ाने से जो पहले मॉलिक्यूल रिएक्शन में पार्टिसिपेट नहीं कर रहे थे वो भी अब पार्टिसिपेट करेंगे, उनको भी एक्टिवेशन एनर्जी मिल जाती है और वो रिएक्ट होके प्रोडक्ट में चेंज हो जाते हैं, राइट? So this is a way how increase in temperature increases the rate of reaction. Okay, so here when you talk about Arrhenius equation, K is equal to A e raised to minus EA by RT. So this EA by RT stands for fraction of molecules having energy greater or equal to greater or equal to activation energy, greater than or equal to activation energy. This e raised to minus EA by RT, this corresponds to fraction of molecules having energy greater than activation energy, right? So this is a way how we can explain the temperature dependence of rate of a reaction using this Maxwell Boltzmann distribution curve. In the examination also this curve has been asked for 2 marks. Draw the Maxwell Boltzmann distribution curve for temperature dependence of a rate of reaction, right? आपको ये ग्राफ ड्रॉ करना है, मेंशन करना है x एक्सिस और y एक्सिस पे क्या है, t ग्राफ और t plus 10 ग्राफ ड्रॉ करना है, energy of activation, and you have to show this shaded form. Okay, dark one and light one. इससे पता चलता है कि पहले मॉलिक्यूल कितने थे एक्टिवेशन एनर्जी के बराबर जिसकी एनर्जी थी, और बाद में कितने मॉलिक्यूल बढ़ गए जिसकी एक्टिवेशन एनर्जी है, राइट? सो दिस इफ यू ड्रॉ यू विल गेट 2 marks. Okay, now if I take the Arrhenius equation, K is equal to AE raised to minus EA by RT. If I apply logarithm, natural logarithm, I'll get ln of K is equal to ln of A, and this one e raised to minus EA by RT will become minus EA by RT. 10 raised to सम पावर है जैसा log लेते हैं तो log of 10 is 1, तो यहाँ पे ln of E will become equal to 1. So you will be left out with ln of A minus EA by RT, right? So this will be the thing you will get over here. Now if I take this Arrhenius equation at two different temperatures, right? I'll take at two different temperatures. That time what happens is, suppose this is at particular temperature, I'll write at a temperature T1, this rate constant will be given as K1. At a temperature T2, we can write ln of K2 is equal to ln of A minus EA by RT2. It is Arrhenius factor, it will be constant. R is a gas constant, that is also constant, and here EA is the activation energy for a given reaction. Okay, so if you subtract equation 2 from equation 1, what you will get is ln of K2 minus ln of K1 will be equal to ln of A minus EA by RT2 minus ln of A minus EA by RT1. Ln of K2 by K1, I can write it as ln of K2 divided by K1. Ln of K2 minus ln of K1 can be written as ln of K2 by K1 because it is a logarithmic operation. Log of A minus log of B can be written as log of A by B. And here this ln of A minus ln of A will be cancelled out. You will be left out with minus EA by RT2, minus of minus will become plus EA by RT1. Okay, what is common over here is ln of K2 by K1 is equal to, I will take out EA by R common, EA by R common, and in the bracket you will be left out with minus 1 by T2 and plus 1 by T1, or I can write 1 by T1 minus 1 by T2, right? You will get like this. Or if you take further simplification, you will be getting ln of K2 by K1 is equal to EA by R T2 minus T1 divided by T1 into T2. This is the relationship for activation energy of a reaction at two different temperatures, right? So this ln, if I convert into log, what will happen? That time we'll be writing it as 2.303 log of K2 by K1 is equal to EA by R T2 minus T1 divided by T1 T2. Okay, or log of K2 by K1 is equal to EA by 2.303 R T2 minus T1 divided by T1 T2. Okay, so this is the formula to calculate activation energy of a reaction at two different temperatures, right? So K2 and K1 are the rate constants at two different temperatures, T2 and T1. EA is the activation energy expressed in joule per mole or kilojoule per mole, and R is the gas constant where we take its value as 8.314 joule per Kelvin per mole, right? So इसको आप मल्टीप्लाई करके डायरेक्टली लिख सकते हैं क्योंकि R की वैल्यू कितनी होती है 8.314 joule per Kelvin per mole right? When you multiply 2.303 into 8.314, you will be getting log of K2 by K1 is equal to EA by, multiply karo 2.303 into 8.314, you will be getting the answer as 19.147. Can keep like this also, okay, because it is understood क्योंकि ये वैल्यू तो चेंज होने वाली नहीं है और इसके साथ यही पार्ट मल्टीप्लाई होने वाला है, तो आप इतना लिखने के बजाय 19.147 भी लिख सकते हैं. यहाँ पे सेम एज यूजुअल T2 minus T1 divided by T1 T2, right? So very important formula. Arrhenius equation can also be written in this manner. Arrhenius equation at two different temperatures can be written as log of K2 by K1 equal to EA by R or EA by 2.303 R or EA by 19.147 T2 minus T1 divided by T1 T2, right? Numericals for 3 marks are based on this formula, right? In the next session we'll be doing the numericals on this also. Now if you move back to this relationship, ln of K is equal to ln of minus EA by RT है, right? इसको मैं फिर से लिखता हूं यहां पर ln of K is equal to ln of A minus EA by RT is there, so I'll write it as EA by R into 1 by T, EA by RT. So it is of the form Y is equal to mx plus c, right? So here along y-axis ln of k is there, along x-axis 1 by t I have taken, and m is the slope. M is the slope, okay, that is negative slope. M is equal to nothing but slope. It is equal to what? Minus EA by R, right? And the intercept is ln of A. Intercept is ln of A. Okay, so slope is equal to minus EA by R. When you take ln of K, when you take log of K, ln of K can be changed into log of K by writing 2.303 log of K is equal to, you will get log of A minus EA by RT. So when you take like this, what happens is slope will be equal to minus EA by 2.303 will come on this side, it will be 2.303 R, right? So this part we call it as slope. स्लोप कैलकुलेट करना है ग्राफ से तो आप ले सकते हैं माइनस ई ए बाय आर इफ नेचुरल लोगैरिथम इज गिवन, if base 10 logarithm is given, log logarithm is given, base 10 logarithm log values are given, that time slope is calculated equal to minus EA by 2.303 R, right? So यहाँ पे ग्राफ है, ये भी ग्राफ 1 मार्क के लिए पूछे हैं. Plot a graph of ln of K versus 1 by T for the activation energy of a reaction. So you have to draw like this. Mention ln of K along y-axis, x-axis 1 by T, and you have to mention the slope. Slope is equal to minus EA by R. अगर यहाँ पे log ले रहे हैं तो slope is equal to minus EA by 2.303 R, right? So remember this one also. Okay. So in next session, we'll discuss some numericals on this calculation of activation energy, right?